Welcome, everybody. We're just going to give it a minute so that everybody who's already here can join. Okay, so maybe we will start. Welcome, everyone. Thank you for being here. So today's talk is by Modibo Camara, who's going to talk about eliciting informed preferences. This is joint work with Nicole Immorlica and Brendan Lucier. We also have panelists here today. We have Agathe, Pernoud, Antonio Penta. Geoffroy de Clippel may join us later. The usual format, 1 hour talk plus 15 minutes for Q&A. We normally stop recording at that point, and depending on what's the equilibrium, we might have a little bit more chatting and discussing afterwards. Just a final reminder that next week we have Jonathan Liebgober, who's going to talk about implementing evidence acquisition time dependence in contracts for advice. So without further ado, Modibo, the screen is yours.
Thank you very much. And thank you as well for the discussants and everyone for coming. So the starting point for this work, there are two starting points. One is this idea of revealed preference, right? The link between choices that we can observe and underlying preferences that we can't directly observe. Very important idea in several areas of economics, including welfare economics and empirical economics. Then we have this other idea, which is the idea that information processing can be costly, right? So the idea that learning one's own preferences about, say, a product or a policy might take time and effort. Now, the issue with costly information processing is that this can disrupt the sort of link that we're used to between choices that people make and preferences that they have. And just to be clear, when I talk about preferences, what I mean are going to be preferences that someone would have if they were fully informed. So for instance, if they took the time to process all the available information about a product, what would be their willingness to pay? So the research question that we're going to be pursuing here is going to ask whether it's possible to restore this link between choice and preferences by being clever about how we set up the choices. So more precisely, when people find it costly to process information, are we still able to learn about preferences through well-designed choices? So what I'm going to do next is I'm going to be a little bit more clear about the question by telling you a bit about the way that we formalize it. So suppose that there's a researcher. The researcher wants to learn about a population. Researcher could be an academic running an experiment. It could be a market researcher employed by a company. Or as we'll see sort of in a little bit, it could be a planner who's trying to deliver some good outcome for a population. The population has preferences that are unknown to the researcher. Those preferences might be heterogeneous. They might be correlated in complicated ways. The researcher is going to recruit N agents, so a large number of agents, to participate in a mechanism. So mechanisms like an experiment, essentially, the agents are going to send messages to the mechanism. Based on the messages sent to the mechanism, they're going to get individualized allocations of, say, a product and individualized transfers. Now, of course, we're thinking about a setting with costly information processing. So the agents do not necessarily know their own preferences up front, like their true value from some product, but they're able to learn about their preferences at a cost. And I'll talk a little bit more about what that learning process looks like when we get into the detail of the model. So just to summarize, the researcher faces a robust mechanism design problem where agents have costly information acquisition. So the researcher's goal is going to be to learn something about the distribution of preferences in the population. And the researcher is going to have to come up with a mechanism that's both prior independent, so it doesn't depend on the distribution of preferences, which is unknown, and potentially robust to any ambiguity that the researcher has about the nature of information acquisition from the agents. So in this model, what are the results that we obtain? Well, the results are basically going to characterize the conditions under which particular statistics of the population's preferences are elicitable. So informally, and I'll be more precise later on, we're going to say that a statistic is elicitable. So statistic like what is the average value that the population has for the product, or what is the fraction of the population that's willing to pay whose value exceeds some like fixed price. We're going to say the statistic of the population's preferences is elicitable if there exists some mechanism that the researcher could design such that in every equilibrium of the mechanism, the choice data, so the messages sent in equilibrium, are going to identify the statistic of interest. What we show in our first two theorems, which are going to be the ones that I think I'll spend almost all of my time on today. The first two theorems say that we can sometimes elicit the population's average preference, so like the average value for the product in the population, but essentially nothing else. So for instance, if you're interested in the fraction of the population whose value exceeds some price, which is like an informed analog to quantity demanded, that is something you would not be able to elicit. So these results say that what the researcher can learn when information processing is costly is quite limited. Now, we don't want to, of course, end the paper on a negative note. So what we also do is we think about the ways in which eliciting the population's average preference, the limited thing that we are able to do, the ways in which that might be useful. And it turns out that there's a big class of applications where eliciting the population's average preference is sort of sufficient, is the only thing that you would want to do. And that class of applications is in social choice. So what we do as an application of these results with some additional work is we show that there exist social choice mechanisms under some conditions that are efficient, and in particular efficient in a way that's robust to costly information processing, right? So we think about this if you're designing an election and you really had a lot of freedom to shape elections in the way that you'd like, you can think about these mechanisms that we propose as a way to combat uninformed voting. How do we incentivize voters to acquire information about the policies and candidates that are asked to vote on? So as I mentioned, I'll spend most of my time on the first two results, theorems 1 and 2. If we have time, I might touch on the social choice application, but otherwise I'm happy to talk about that offline. So I'll talk about related literature in a second, but let me pause here for 5 seconds and see if anyone has any questions at this point.
Actually, I have a short question clarification. When you say preferences, that is sort of about the value of the good or whatever is the problem. That's not part of the information acquisition cost. You don't mean that?
Yes, so we're not trying to learn about the information acquisition cost, right? And of course, there's a bunch of work on thinking about how do we learn about the sort of the nature of information acquisition, the costs associated with that. But our goal here is really just to learn about the preferences in the population.
Modibo, this is something that maybe you want to discuss at the end. So just to put a pin. So you're using robustness in the information that they might have. You don't want to be Bayesian here, which is a choice of a modeling choice that you've made. But somehow you're gonna, I suppose, tell us that there's good information about what the cost of acquiring process is, right? So you could be actually agnostic about that. You don't know exactly how much it's going to cost to acquire the information, or you could be, say, Bayesian, you will have beliefs on that and whatever, or it could be common knowledge or so on. So you could have made different choices here. That's what I suppose what I'm trying to say.
Yeah. So, and as you said, like when we get into the model, it might also be a bit more clear what are the precise choices that we're making. But you can think about it this way. So our results apply even if you think that the planner knows the information acquisition technology. So like if you think about the distribution of costs of information acquisition in the population, it's fine for the planner, for the researcher to know that. We also sort of show that at least our positive results, which are the ones you'd want to extend, are robust to the nature of the information acquisition technology, subject to assumptions that we make. Now, when it comes to the distribution of preferences, so yes, we are not taking a Bayesian approach to thinking about the distribution of preferences. In a sense, we're taking a frequentist approach, right? We're asking, given some I mean, we're not going to make many assumptions, but given some class of possible distributions, can we come up with an estimator that's going to identify the distribution within that class? So the identification question that we're asking here is essentially frequentist, and what that translates into is a robust mechanism design problem. Okay, any other questions before I move on? Great. Feel free to interrupt as we go through. So, okay, I'll just touch on related literature briefly. I'll probably come back to this a little bit once we get into the details of the model and results. So just to say, there is, of course, a long tradition of work on preference elicitation. You can broadly divide this into two parts. You can think about eliciting willingness to pay, or tastes, and you can think about eliciting beliefs. Our focus here is going to be on eliciting willingness to pay, but we're going to also use some of the tools, proper scoring rules developed for eliciting beliefs as part of the mechanism, which we'll talk about later. Large, diverse body of work that thinks about preference elicitation through betting. So we're going to see that betting is going to play a somewhat simpler but still important role, similar to these papers, in the positive results that we obtain. And I'll sort of compare our mechanism with some of the mechanisms that you might be familiar with, like full surplus extraction and basic truth serum. A lot of work on games with information acquisition, including applications to mechanism design, and including by one of our discussants today. Several papers, actually, but I didn't have space to include all of them, so check them out. So in particular, we're going to be thinking about, not for all of results, but our most general model, we're going to be thinking about designing mechanisms that are robust to the kind of information that agents can acquire. And this is going to look similar in a sense to Gabe Carroll's work on contracts and in particular contracts for information acquisition. The assumptions that we're going to be making are different, but the idea of you have some known action that the agent can take and you want to be robust to unknown actions, that's going to come through. And then finally, when it comes to social choice, which I will not be discussing probably that much today, there's been a historical focus on how do we combat strategic voting in elections. There's been less focus on combating uninformed voting, but there has still been work in the past 2 decades. And we're going to be proposing mechanisms that sort of try to combat try to deal with the issues associated with uninformed voting. Cool. So what I'm going to do for today, I'm going to walk you through the model. Then I will give you the negative result that talks about the statistics we cannot elicit. Then I'll talk about the positive result that talks about eliciting the average under some conditions. Again, I'll probably skip the application and we'll conclude. Okay, so let's get started with the model. So first thing we need to talk about are preferences. So you can think about the researcher as recruiting some sampled agents. Okay, and just to be concrete as we go through the model, let's think about one particular application. So let's think about a market researcher that's hired by the company OpenAI, right? So the creator of ChatGPT. And what the market researcher does is it sort of goes to the sort of set of potential customers and randomly select some of them and ask them to sort of come in for a focus group or to participate in a survey. We're going to say that there are N agents. That's the sample size. But of course, we're talking about identification, so we're going to let the sample size go to infinity. Now, each agent can receive an individualized allocation. Just for simplicity, for the talk, we're going to focus on sort of binary allocation. So you either receive a product or you do not receive a product. Again, just to fix ideas, you can think about the product as being GPT-5, the new improved version of GPT-4. Now, consumers or the agents, agent I, will have some value VI, which just reflects their utility from the product. So like how much value they would get from a year-long subscription to GPT-5. Of course, this is something that the consumer, being unfamiliar with this new product, might not immediately know. One thing to note is we assume that the values are in some closed interval. You could, if you want to assume that the value from the product is non-negative, that's fine. But just for generality, we're going to allow the possibility that your value is negative. The outside option, sort of not receiving an allocation, you're going to get utility 0. You can think about that as like your value from GPT-4, which you currently have access to. Okay, so let's talk about information acquisition. Here I'm going to have to introduce a couple different things. And the reason why I'm going to have to introduce a couple different sort of concepts is because we want a model that's going to be rich enough to capture complicated forms of correlation and heterogeneity in the population. So the first thing we need to talk about are private types. So agents I's private type is essentially their initial information. You could think about something like their profession. So if I'm a translator or I'm a software engineer, then I might have sort of higher than typical value for GPT-5 because it might be particularly good at those tasks. So my type might be correlated with my value. There will also be a hidden state. Okay, hidden state you should think of as like the capabilities of GPT-5, right? You don't necessarily know this up front, but in principle, there's some sense in which GPT-5 might be really good at translation and like okay at coding tasks and like really bad at writing. Right? That would be one possible state realization. So the state is going to be something that could, in principle, sort of systematically affect people's preferences. And we're going to be assuming that the state is going to be drawn from a state distribution, ST. So S for state, D for distribution. Now, so we have values that we introduced on the previous slide, and we have types. Values and types are going to be drawn from a preference distribution. And that preference distribution could depend on the state. So if GPT-5 is in the state where it's really good at translation tasks, then it might have induced a different distribution over values than if GPT-5 is really bad at translation tasks. Okay. To learn about one's own values and potentially other sort of elements of the model, agents can acquire signals. So agent I acquires signal SI. The benefit of acquiring a signal is that you get a signal realization. The signal realization can depend on the state, your type, and your value. So you already know your type, but it depends on the type means that the same signal could be more or less informative for different kinds of people, right? So for instance, if you're a translator translating English to Spanish, then and you ask GPT-5 to translate an English paragraph to Spanish, you might be particularly well equipped to evaluate how good that translation was. And so you might derive more information value from that signal. Whereas if you're not a translator, you don't speak Spanish, asking GPT-5 to translate an English paragraph to Spanish, it's hard for you to evaluate whether it's a good translation or not. Yes, so the signal could also depend on the state. So you could learn something about the quality of GPT-5 at translation tasks. And of course, the signal could tell you something about your value. And then last thing on this slide, we have costs of acquiring signals. So a cost function CI is going to determine the cost for agent I of acquiring the signal. Cost functions can be random. They're going to be drawn from a cost distribution, CD. Note that different types might have different cost distributions. Right, so some types of agent might sort of have systematically higher costs from acquiring information than others. Okay, so
sorry.
Yes.
Can I ask
please.
a question?
Yeah.
So I'm curious as to why you introduced this hidden state instead of just a joint distribution over the values. So is the idea that by having this, then you can force that the only way I can learn about others is through that common component in some sense? So is that the only thing it's doing, or is it doing more?
Yes. So I think we could probably define things more formally. Sorry, not more formally, more generally. So just have some arbitrary joint distribution. So as long as we're able to sort of define what it means to sample agents from that distribution, right? Sample them randomly from the broader population, then maybe we could get away with not having this hidden state as like an explicit variable. I'm going to make some assumptions later. So I'm going to make some finiteness assumptions that will be more convenient to state in the setting where I have a state explicitly. But I think in terms of me learning about other people via the state, right? The idea here is I'm one person, I'm an agent, who is asked to participate in the survey. I don't know the other agents that are participating in the survey, right? So if I want to learn about what those other agents are thinking or doing, what I would need to learn is I would need to learn about this preference distribution, PD, right? And what we're doing here is we're associating preference distribution with a state omega. So in principle, we could replace hidden state with preference distribution and have a prior over the distributions.
Okay, thanks.
Okay, so
Modibo, just a clarificatory question. So when you say independent draws on the right-hand side, is that just an example like the other lines, or that's what we are assuming?
No. So the they are sort of IAD draws from the preference distribution. So the idea is we have a population of people. We're taking a random sample of agents to participate in our experiment. And the values across the different agents could be correlated, but if they were correlated, it's because of the state, right? So we could be in a state of the world where the preference distribution, everyone has very high value. We could be in a state of the world where everyone has very low value. So there could be correlation between agents, but not conditional on that state. Does that answer the question?
So the preference distributions are IID.
So there is a single preference distribution. So you could think about this as a demand curve. Omega is going to different values of omega will lead to different demand curves. But once you fix the demand curve, what we're going to be doing is we're going to be randomly sampling agents from the population that generates the demand curve.
Okay, thanks.
Sorry,
so just you go ahead, Antonio.
Okay, one question was the same. I understand these are conditional independent conditional states.
Yeah.
And the second one is about the calligraphic S. Is the set of signal the set of all, conditional distributions on those three?
Yes.
Okay.
Sorry, so I was saying yes in my processing of your question. So S right now is arbitrary. What I'm going to assume later is that it's a finite set. For the talk, I'm mostly going to focus on the case where it's a binary set, and I'll tell you what that looks like. In general, we can think about S as being a larger set as long as it's finite and it includes a particular signal, and I'll tell you about that. So in other words, right now, just think about S as an arbitrary set. It could be restricted relative to the set of all possible signals, and I'll tell you exactly what structure we're imposing in a few slides.
Okay. One last thing about the cost functions. Again, for now, should I think about arbitrary functions from the set calligraphic S to R, or do you want to think about something, I don't know, that's increasing informativeness?
Sorry, my connection interrupted a little bit. Would you mind just saying that again?
So the cost functions, are these also, I guess, arbitrary function from calligraphic S to R, perhaps increasing in informativeness, Blackwell ordering?
Yeah, so right now, think about them as an arbitrary function from S to some real number. And I will tell you what structure we're imposing on that as well in a few slides. Okay. So please let me know if there are any more questions at this point. I know I'm throwing a lot of different objects at you in this slide. And sort of understanding how they're all related together can be a bit challenging. So otherwise, let me talk about just what prior knowledge we're assuming in this model. So one thing that's going to be helpful to refer to is an information model. You could also call this an information acquisition technology. It's maybe a little bit more than that. So the information model is going to consist of the set of types, the set of states, the set of signals, and the cost distribution, CD. Now, I should also mention the information model excludes the preference distribution and the state distribution. Right? So you could think about the information model as capturing everything except for the distribution over demand curves in the population. Now, in the talk, we're going to assume that the researcher knows the information model. So you basically know what signals are available to the agents and how their costs are distributed in the population. It's not necessary for positive results, but making this assumption will strengthen our negative results. We're going to maintain a common prior assumption among the agents, right? So we're going to assume that the agents know the information model, but they also know the state distribution and the preference distribution, right? So I might not necessarily, so basically I as an agent, I know how my value is going to be correlated with your value, right? Even if I don't know my value, and even if I don't know the realization state. So from the research perspective, we're going to be robust to the state distribution and the preference distribution. For the agents, we're going to maintain a common prior. Mechanism. So let me just talk about the mechanism and the mechanism design problem and the timing of the game. So first, the researcher is going to announce an allocation rule and a transfer rule. Agent I will then observe her private type theta I, as well as her cost function Ci, and then on that basis acquire some signal Si. Then agent I will observe the signal realization, and based on that, send some message Mi. The researcher will assign an alternative and transfers to the agents based on the message profile. And then finally, the agent's utility will be the value they get from the product, provided that it's allocated, minus the cost of information acquisition, plus any transfers that they receive. And I'll pause here again for a moment in case there are any questions.
Can you just talk a bit about as to why the signal realization depends on theta I if theta I is observed already?
Yeah, so you could imagine so the same signal being more or less informative for different people. So for instance, like the example that I gave before, you could think about someone, the type sort of indicating whether you're like you speak Spanish or not, right? So if you have if the signal you're requiring is like the action of typing in an English paragraph in GChat and GPT-5 and asking it to translate, right? If you're a translator, that's going to be an informative signal because you can read the Spanish and decide whether it's good. If you're not the translator, if you don't speak Spanish, the signal realization will just be basically white noise, right? And so you could think about the SI is just outputting 0 all the time.
I see.
Yeah. So just another way to allow for additional heterogeneity in the population. Any other questions at this point? Okay. So last 2 slides of the model. So I need to tell you what it means, what are statistics and what it means to elicit them. And then I need to tell you what is the structure that we're going to impose on this problem, the assumptions that we're making, and then we'll get into the results. So we're going to refer to what we call sigma statistics. These are basically just moments of the preference distribution. So the preference distribution is sort of given the realized state omega, there's some distribution of preferences in the population, and we care about the expected value of the function sigma applied to Vi. Now, fix an information model. Again, this is like the information acquisition technology. We're going to say that a sigma statistic is elicitable if there exists an estimator, sigma hat, and a sequence of mechanisms, so the sequence depending on the sample size n, where for all distributions, state distributions and preference distributions, and all equilibria, or sequences of equilibria associated with the sequence of mechanisms, the estimator applied to the messages sent in equilibrium will converge to the value of the sigma statistic. So there's a lot going on in that definition, or at least it has several parts. So let me just say it again. We're going to say a sigma statistic is elicitable for a given information model if we can come up with an estimator that takes in messages sent in equilibrium. If we can take the estimator and come up with a sequence of mechanisms, sequence as the sample size grows, where for all distributions and all equilibria, our estimate is going to converge to the true value. So in other words, the estimator is consistent. Let me know if there are any questions before I move on. So this is going to be, of course, a critical definition in our results.
Modibo, can I ask a question? I mean, this is very abstract and a bit unusual, so maybe I'm missing something, but I'm interested about this all equilibria. So we're requiring full implementation in some sense. Are we, in the usual sense, going to let go of things like the revelation principle? I don't know, is this relevant here? It's so different of treatment of mechanism design that I don't know. But when I hear when I say all equilibria, I immediately go, oh, the revelation principle goes out of the window. But maybe, I don't know.
Yeah. I mean, so we're not going to rely on a revelation principle. So, you know, perhaps the fact that we're focusing on full implementation is part of that, but you know, it's not something that we rely on even if we're I'll tell you about a result that's focused on partial implementation. So even for that result, we're not going to rely on it. But yeah, so we are focused on full implementation. That is important, right? So I can tell you like a little bit about how results change if we focus on partial implementation, but ultimately it's an open question. The reason why we focus on full implementation, and this might become a little bit more clear later on. No, actually, I think I can make it sufficiently clear briefly now. So if you focus on partial implementation, there are a bunch of seemingly unrealistic mechanisms that arise. So one thing the designer could do is they could go to the agents and say like, hey, tell me your common prior. So tell me the state distribution, the preference distribution, or the preference distributions. And if anyone deviates from this common report, we're going to punish you all, right? And so there's going to be an equilibrium where you learn the state distribution and the preference distribution. Now, this doesn't mean that the problem is trivial for the researcher. So it's still, potentially a challenging problem to figure out how to elicit the statistic of interest because of the kinds of correlation you can have in the population. But it does it does get rid of the desideratum that we have of coming up with a prior independent mechanism, a sort of mechanism that's robust to the distribution. So one reason to focus on full implementation is to get rid of mechanisms like that I don't find particularly plausible. But we'll see again where it comes up when I tell you my negative result.
Modibo, I had a very related question, and you partly touched upon that, which is that like why is so what's the motivation behind like focusing on robustness with respect to equilibria? Because it's totally understandable that robustness with respect to state and preference distribution is something the researcher would be interested in. But when we are also adding robustness with respect to equilibria, which is, I mean, the result is very negative and all that. So is that all that your justification is, which you described about triviality and all that, but there is some other motivation?
I mean, so the way that I think about it is we have this classic literature on preference elicitation. That literature does not require, it does not require us to assume favorable equilibrium selection. It does not require sort of us to impose structure on the distribution. It doesn't require a lot of things. And so it's natural for us to start with sort of the setting that we're able to solve very easily in the classical model of preference elicitation, where there's not cost of information processing, and ask, can we still do this when there is cost of information processing, right? So for us, it seems natural to sort of start with the level of robustness that we're used to. And then if we need to add additional assumptions like favorable equilibrium selection to make progress on this question, maybe that's something we can justify. But that seems to us like a next step after first evaluating the question that we were able to solve in the classical model. Does that make sense?
Perfect, thanks.
Sorry, just one clarifying question. You mean for all states omega?
Say that again?
A quantifier on omega. I mean, for all states, you want this identification, I guess?
Yeah, so you're referring to, do you see this highlighted? Yeah, so this is the realized state.
Okay, so for all realized states, I want to be able to identify the corresponding.
Yeah, so for, yes, yeah, that's right. Okay, cool. So again, let me know if there are any questions. It's, I think, important to make sure that this definition is clear. Otherwise, let me tell you what assumptions we're going to be posing. So first assumption is we're going to make everything finite. So we will make every time we have an opportunity to make something finite, we're going to make it finite. So we're going to make the type space finite, the state space finite, the signal space finite. We're also going to assume that the type space has at least cardinality 3, right? And if you want, I can sort of point out where that's going to come in later on. The cost distribution will have finite support, and the sigma statistics will have at most finite discontinuities. If you're thinking about something like quantity demanded, it is important to think about sigma statistics with discontinuities, but I can't think of any that have, interesting statistics that have infinite discontinuities. So that's the first assumption, everything finite. The second assumption is going to be, in my view, more substantive. So this is going to be a sort of a stronger assumption than we need for most of our results, but let me just say it as it is, and then I'll tell you how we can generalize it. So assumption 2 says that basically information acquisition is binary. So each type theta I, each type of agent, has exactly 2 signals that are available at finite cost. One is an uninformative signal, right? This is basically you're deciding not to acquire any information, and the other one is a revealing signal. And the revealing signal tells you your value. It could tell you other things. It could tell you about the state. It could tell you, whatever. but in particular, it tells you your value. So the simplest version of this is I pay some cost to learn my value. And if I don't pay that cost, I don't learn anything beyond my initial information as captured by my tag. So our positive results hold in a much more general model. We're thinking about the set of signals as being arbitrary with two conditions. First, the set of signals must include the revealing signal, right? That is to say, if I process all of the available information, then I'm able to learn my value. And if I have access to a signal A and a signal B, then I can sort of acquire a combined signal that combines A and B at a cost that's no greater than the sum of the costs of individual signals, right? So subject to that structure, we can, the positive results that we have are going to be robust to, any kinds of signals that the agents might have, including ones that acquire, partial information about VI or ones that learn about the state omega without learning about VI and so forth.
Presumably, you have some sort of monotonicity here, right? That you're going to exclude signals that are more expensive and less informative, I suppose. Right?
That's kind of naturally going to arise that the agent won't acquire those kinds of signals, but it's not something we need to impose. It would be, of course, natural to impose, but it's not something we need. Any other questions before we move on?
Yes. I'm not sure how naive or fair this is, so feel free to tweet it.
Yeah.
But I mean, elicitation here is about the values that are not necessarily known to the agent. So, I mean, it's not obvious. I mean, unless they acquire information, I guess behavior is not necessarily going to be measurable spectrum to elicit. So, let's say I understand that the main result is negative, but what could make us think that there would be any hope if behavior is not measurable spectrum?
Well, so I guess what I find interesting is that, although our results, like our first result is very negative, there's a lot that you can't do, right? Including learning statistics that are, very natural, like quantity demanded. But it's not hopeless. You are able to learn something, right? And so, I think the fact that you are able to learn something is you are able to learn something, and it depends on of course the person who's looking at the results. But for me, a priori, I'm not sure that I would have guessed sort of the specific statistic that you are able to learn, right? So I do think it's interesting to sort of understand what is it about the average that makes it amenable to being learned, and what is it about other statistics that make it difficult to learn them. And then I think also our results give you some sense of what is the additional structure that you would want to impose on the model in order to make progress in eliciting other kinds of statistics. Because at the end of the day, what is, I think, of greatest interest is coming up with methods motivated by reasonable models that help us learn things about, say, quantity demanded by an informed population.
Just to be clear, at the moment, there is no assumptions about, let's say, in the event in which nobody acquires any information, there are no assumptions that are linking agents' expectation VI given just theta I and no extra sigma, and the true expectation, right? I mean, they did not know the true expectation.
They do not know the true expectation of what?
VI.
VI? It depends. And so are you talking about the expectation conditional on the state or the ex ante expectation?
Conditional on the state.
Yes. So if there are two states, A and B, the agents would know what is the sort of average value in the population conditional on A, what is the average value in the population conditional on B, but they won't be able to say what is the average value conditional on the realized state because they don't know whether it's A or B.
Thank you.
Okay, so let us move on to the negative results. So I'm going to say that any statistic other than the average is not elicitable. To formalize that, I need to tell you what the average is. So I'm going to say that a sigma statistic is an average if sigma is some affine function of VI. Right? So if we think about the population's average value, if the statistic is just some affine transformation of that, we're going to say it's an average. I'm also going to want to introduce a sort of non-triviality condition. So I'm going to say that an information model is non-trivial if the revealing signal has positive cost with positive probability, at least for some type. So what would trivial mean? Trivial would mean that every agent with probability 1 has 0 cost of acquiring information, which is just the classical model without costly information processing. So in that model, we know that we're able to elicit anything we like. And so what we're saying is cut that part away and focus on any non-trivial information model. So theorem 1 says, fix a non-trivial information model. If a sigma statistic is not an average, then it is not elicitable. I'll give you some intuition for this result in a moment. Let me sort of just reiterate and highlight 3 aspects of the model that contribute to this negative result. So in particular, these are things that if you changed, you might be able to overturn the result. So one thing is, if you added more structure on the preference distribution and state distribution, you might be able to do better, right? So like this is a non-identification result. With any non-identification result, if you add more structure, if you add more assumptions, you're potentially able to do better. Second, we talked about multiple equilibria, right? So if you're willing to assume favorable equilibrium selection, you might be able to do better. So we'll see a concrete example of how you can do better in a couple slides. In general, it's not obvious that you would be able to do better, but you might be able to. And then third, we're focused here on exact identification. So, the estimators that we sort of require the researcher to come up with are consistent. They converge exactly to the value of the statistic. If we were allowing for partial identification, like let's say we just wanted some informative bound about the statistic, then we might be able to do better. So, for example, if we had an information model where 99% of the population had 0 cost of information acquisition, right, then you would think we'd be able to learn basically any statistic within like a pretty good degree of accuracy, right? So here we're focusing on exact identification, but a very natural direction to think about to get more positive results would be partial identification. Okay, next, unless there are any questions about the results or what I just said, I'm going to talk about intuition.
Quick question, the direction of the if part, so presumably it doesn't go the other way. Is it trivial that you wouldn't have a characterization or a...
So I'm going to, once we finish talking about the negative results, once we talk about the, if I'm understanding correctly, once we talk about the positive results, then we're going to be basically saying, what are the conditions on the information model such that you are able to elicit the average?
No, but I guess what I'm asking more directly is, if a statistic is not elicitable, is it necessarily not an average?
No, there are going to be information models where you're not able to elicit the average either.
Okay.
So again, let me know if there are any questions. Otherwise, I'll dive into intuition for theorem 1. So it turns out that the hard case for eliciting statistics other than the average is a case that might look kind of easy. And indeed, it will be a very easy case for eliciting the average. So just to be concrete, let's take as an example a situation in which everyone's values are drawn IID from a normal distribution with mean A and variance B squared. And let's suppose that the signal costs are sufficiently high, which, in this case, you can think of them as being like, on the order of or higher than the uncertainty B squared. Now, let's suppose that the researcher's goal is to learn the variance B squared. There are 2 approaches that you could take. So let me start with the first approach and try to give you a sense of where that approach is going to go wrong. So suppose that you come up with a mechanism and an estimator that at the end of the day, the estimator relies on willingness to pay data, right? So like the BDM mechanism, which we'll talk about a little bit later, this is a way of eliciting willingness to pay. By willingness to pay, what I mean is not the actual value of the agent. What I mean is the expected value conditional on the information that they've acquired. So this kind of data is easy to collect. let's think about estimators that rely on it. Well, the first thing to note is that in this specific example, agent I will not acquire information just for the purpose of learning about the product, right? So the idea is that if the costs are high relative to the uncertainty that you have about your value, just offering the product at some price and asking the agent, hey, do you want to buy it at that price? The agent could, improve her, decision-making around whether to get the product or not by acquiring information, but the cost of the information is going to be roughly the same or greater than the benefit that they would get from sort of influencing their allocation in the right way. So in other words, just for the purpose of learning about the product, agent I is not going to be sufficiently incentivized to acquire information. Now, of course, you might still think that agent I will want to acquire information for other reasons. So you might acquire information in order to predict the messages sent by other agents, which at the end of the day can affect your transfers, which might be quite large. So what we argue is that even in this case, agent I will not acquire information for the purpose of predicting other agents' messages. And the reason is because of the independence, right? So the only private information that I might have in this simple example is my value. My value is independent of the other agent's private information, such as their values. And so me learning my value is not going to help me predict other agents' private information, and therefore it won't help me predict their behavior. Okay, so because of that, so we have agents that don't acquire information. Their willingness to pay in this simple example, if they don't acquire information, is just the mean A. Learning the mean A doesn't tell you anything about the variance B squared. So you can already see here that if what I care about is learning the mean A, then this is not a problem at all. This example is trivial. But if what I care about is learning B squared, then I'm not going to be able to sort of take the first approach here. Now, there are other approaches you could take. You can imagine a bunch of different approaches. Here's sort of a fairly obvious one. Suppose that I ask the agents to directly report the variance B squared, right? So this is like what I was talking about before, where agents are reporting their comment prior to the designer in advance, right? And then what you can say is, okay, if there's any discrepancy in the reports by the agents, I'm just going to punish everyone. Now, the issue with that, as I mentioned before, is this is going to have non-truthful equilibrium, right? There's an equilibrium where agents will coordinate on the true value. There's an equilibrium where agents will coordinate on the false value. And if we care about robustness to potential equilibrium that agents play, this mechanism is not going to work. Now, you can imagine a bunch of other mechanisms, and particularly you can imagine mechanisms that depend on the information model in a more precise way. And indeed, this particular example is not one in which we're able to prove our negative results. But we can build on the ideas that we have in this simple example to construct counterexamples for any information model and any statistic that's not equal to the average. So I'll pause here in case there are any questions about the intuition for our negative results. Otherwise, I'll move on to our positive result.
Yeah, can I ask a question? More like rephrasing of what you said and then a question. So the way I interpret what you said is that at the end of the day, because of the equilibrium selection robustness, we kind of have to focus on the case where no one learns anything. And if we fix that no one has learned anything, the only thing we can elicit is your prior expected value, the prior expected value.
In a sense, yeah.
Okay, perfect. So which is true here because people have quasi-linear utilities and you care. So if you change the model slightly and it's your value is convex in X or something else, with the same intuition hold, that at the end of the day, what matters is you think of the case where no one learns, and the thing you can elicit is that the prior, given your payoff for the allocation, which might not be linear, I'm trying to go beyond the linear case, that would be that particular statistic. I'm sorry, maybe I'm being very unclear, but
Oh, no. So let's see. So, I mean, in principle, all of our results apply when you have multiple alternatives, right? We still assume finiteness, but you could imagine having sort of alternatives that sort of say, okay, you have 1 unit, 2 unit, 3 unit, whatever of the product up to some upper bound. And then you could imagine sort of, imposing structure on the sort of utility function, convexity or concavity. And I mean, of course, that's not the case that we look at because we don't impose that kind of structure.
Yeah.
I won't be able to sort of say anything to a meaningful degree of reliability. I think in this negative result, I mean, the reason why it extends to the case with multiple alternatives is because it's, we care about robustness to a wide variety of preference distributions. And so in particular, we can focus on preference distributions that only put value on the first two alternatives.
Okay.
So I would need to think more about whether it would be possible to sort of extend this negative results given the structure that you have in mind.
Okay, thanks.
I think maybe the most natural way would be, like a special case of sort of a convex preference would be, you have a zero value from, units 1 through k, and then you have like some unknown positive value from unit k plus 1, and then maybe it would look like the sort of the binary alternative case. But it's something to think about. Cool. Any other questions before we move on?
I just wanted to understand if my intuition is correct based on this example, what you explained. So basically the average is something that the agent can learn for cheap. And if the cost is large enough, then any other moment is something they're just not going to learn. And that's why you can't elicit it. Is that the correct intuition based on this example?
Yeah. So I mean, for this specific example, so the because everyone's value is IID, right? Like your willingness to pay without acquiring any information will equal the average willingness to pay if everyone were informed. Now, of course, if we think about other kinds of distributions, which part of the point of this is to look at more complicated, realistic kinds of distributions of our values, then the average is going to be harder to elicit. But I think that intuition is reasonable for this specific case. Does that answer your question?
Kind of. Like my hope was that the cost being large enough, disincentivizing learning will generalize because of robustness.
Does it generalize?
No, I'm saying that even beyond this example, the intuition of the cost being large enough disincentivizes learning of any other moment. That idea, my understanding is that should generalize because we have robustness. Is that how it goes? Is that why other statistics become impossible to elicit due to robustness? Is that intuition correct?
I mean, so
feel free to not take time for this if it doesn't make sense or whatever. If my
I think maybe we can chat in the remaining period and I guess get a bit more clarification on the question. But so it's not necessarily that the cost being high is a barrier. So for instance, if we had a different distribution where our values were correlated, then we might be able to overcome this sort of high cost of information acquisition by using a strategy like what I highlighted here, where we're trying to incentivize agents to acquire information in order to predict other people's messages in order to increase their own transfers. But the sort of independence across agents shuts that down. And the fact that the cost is relatively high is going to shut down the sort of incentive to acquire information about the product just for the sake of learning about the product. But if that's not totally addressing your question, then I'm very happy to talk about it.
Thank you.
Cool. Okay, so let me talk about our positive results. We're listening to the average. So let me start with a sort of slightly weaker notion of elicitation that corresponds to partial implementation rather than full implementation. So I'm going to say a sigma statistic is weakly elicitable if it's elicitable given best case equilibrium selection. Not necessarily an assumption that I find appealing, but a good sort of starting point for the next results. So the first part of theorem 2 is going to say that if the sigma statistic is an average, then we can weakly elicit it. And here we don't need any sort of conditions on the information model. Now, of course, what we care about in the end is we care about elicitation. So we care about what happens in all equilibria. And so what we sort of show is that under some conditions, you're able to elicit the average. The condition is what we call an informed minority condition. So in the example of OpenAI, the way to think about this would be if there is some proportion of the population that are like early adopters that are intrinsically interested in GPT-5 and willing to play around with it and sort of understand how useful it is to them, then the informed minority condition will be satisfied. If you don't have those kinds of early adopters, then it won't be satisfied. And that condition is going to control whether or not we are able to elicit the average. So more precisely, I'm going to say that an information model satisfies the informed minority condition if every type theta I has some cost that's 0 with positive probability, right? So for every type theta I, there's some chance that they're an early adopter. It could be that for some types, there's a greater chance of being an early adopter than other types, but every type has some positive probability. And so theorem 2b is going to say that the average is elicitable if and only if the informed minority condition holds. So depending on whether you think the informed minority condition makes sense for your application, this could be seen as a positive result, or it could be seen as a very negative result. Okay, so let's see. I have about 4 minutes left. So what I'll do is I will tell you the mechanism that we use to elicit the average, and then maybe give you like a 30-second intuition, and then I'll conclude. So the mechanism is as follows. So it's basically a straightforward combination of two ideas, proper scoring rules and the BDM mechanism. I think what is interesting for me is not the mechanism itself, because it's pretty straightforward. What is interesting to me is why it works. So I'll try to give you a quick sense of that. So just to start, the Becker-de Groot-Marshak mechanism, BDM, it's a simple mechanism sort of widely used in experiments. What it does is it asks agents to report their values, and then it gives them an allocation as follows. So what you do is behind the scenes, you randomly draw a price. And if the reported value exceeds the price, then you sell the item to the agent at that chosen price. Right? So it's like a second price auction where there are two bidders and one of the bidders is just a random number generator. Cool. So the mechanism that we are using to elicit the average is called BDM with betting. So basically, it's the following. So 2 stages. We are going to the agents. We're saying, hey, you are going to participate in the BDM mechanism in a moment. Before you participate in the BDM mechanism, you have an opportunity to predict the average reported values in that BDM mechanism. Later on, after we run the BDM mechanism, we see the average reported value. We're going to reward you if you give an accurate prediction, and otherwise we won't. So more precisely, we're going to ask agents to report their beliefs over the average reported values in the BDM mechanism. We're going to then ask them as part of the BDM mechanism to report their values. And then finally, we're going to give them sort of the allocation according to the BDM mechanism and the transfers according to the BDM mechanism and according to a proper scoring rule, which is used to evaluate the accuracy of their prediction. So just some things to note about here, like the estimator that we're going to use with BDM with betting is just the average reported value as an estimate of the population's average value. So in particular, we're not using people's bets to estimate the population's average value. We're not trying to make inferences about people's private information based on how they bet. The only reason for the betting here is going to be to incentivize certain kinds of information acquisition. If you think that the information you're acquiring is correlated with how other people report, that's information that you will acquire as long as the stakes, as long as the scale of the proper scoring rule is sufficiently large. Cool. So 20-second, a quick intuition. Why does this work? You can imagine 2 sort of extreme cases, one where everyone's value is independent and one where everyone's value is correlated. If everyone's value is independent, then we already saw from the previous example that even if agents don't acquire information, it's fine, right? Even if they don't acquire information, you're still going to be able to learn the average. And so this mechanism will not incentivize information acquisition if everyone's value is uncorrelated. But the nice thing about the average is, in that case, it doesn't matter. Now, if people's values are correlated, then all of a sudden, me learning my value might tell me something about other people's values. So if other people are acquiring information, then me learning my value is going to help me predict how they behave. Okay, so those are sort of very simple extreme cases. Of course, actually proving the result requires a lot more work, but hopefully that gives some quick intuition. Cool. So now I have, I think, a minute. So I'm going to just very briefly conclude. Oh, I need to skip the application. Okay. So the question that we asked at the beginning was, if it's costly to process information, are we still able to use choices to learn about preferences? And the answer that we obtained is that what we can learn is quite limited, but even that limited amount might be quite useful for certain applications. Potential directions that we see is, empirically evaluating this BDM with betting mechanism, exploring other forms of bounded rationality other than costly information processing, and thinking about applications to market research and other areas. Thank you very much, and happy to take any questions.
Okay, so I'm just going to ask Agathe and Antonio if they have any more questions and comments. Agathe, you want to go first if you have anything more?
Yeah, sure. So I'm sorry, it's because of all the questions you went quick on the proof. So I actually have a question about the intuition. So for the independence case, I'm with you. So for the correlation case, what I struggle to understand is why there can't be an equilibrium. If at the end of the day, most of your incentives to learn comes from this betting thing.
Yeah.
Why is it not possible to construct an equilibrium where people only learn about omega? And if everybody only learns about omega, that's good to like guess what other people say, but not good for them to actually learn their true value. Does that make any sense? That's the part I missed.
Yeah. So it's a good question. So if everyone learns omega, right, at that point, sort of conditional on the information they've collected, the agents might make mistakes in how they report. So like their report might be different from their true value because they haven't bothered to learn their own individual true value.
Yes.
But once you learn omega, any error that you have in your reporting is going to be idiosyncratic, right? So my error will be independent of your error, independent of some other person's error. And so once you have idiosyncratic errors, then you have like a wisdom of the crowd effect, where the average
is going to be correct.
Everyone is individually uninformed. The average is going to be well-informed.
I see. Okay, and then follow-up question. Why do you use the fact that you need an informed minority?
That's to rule out bad equilibria that can arise in some cases. So like, for instance, if you have, so like the setting that I've been looking at, that I've been telling you about now, is one in which you have sort of two signals. One is uninformative, one is informative. Let's suppose that the population is homogeneous, right? Kind of like in the example that I told you with the normal distribution. So in that case, you could have an equilibrium where no one learns anything, right? And so it's not useful to me to learn my value to predict other people's values because no one else knows their value either, right? So the informed minority condition is there to kill bad equilibria that can arise for some distributions.
I see, because the assumption is that if there is some probably an informed minority, then the informed minority, I forgot the definition. The definition was that they have zero cost of learning, right? But even if you have a zero cost of learning, you could still choose not to learn. What you're saying is that they have a strict incentive to learn. You see what I'm saying?
I see. That's a good question. So
are we assuming that they're just informed and like the choosing, it's like, which is kind of the informed minority, I guess.
So I guess I mean, so you're getting at the question of tie breaking, right? Like if an agent yeah. So the because we're using we're based on the BDM mechanism. The BDM mechanism is going to provide some like epsilon incentive to learn about your value.
So you have a strict incentive to that. Okay, perfect.
Yeah, but that's a good question.
Okay, Antonio?
Yeah, no, I have mostly a clarifying question as you were talking before. So let's say, in principle, you could design a mechanism where you give rewards for, let's say, guessing the variance of some high number. And I guess the issue with that mechanism is always the existence of some kind of public equilibrium, which nobody would miss for information. I mean, is that the reason why these other kind of scoring rules that target different ones? Is it multiplicity issue?
So yeah, I think the so if we if we think about the BDM with vetting mechanism, right, I talked about these two different cases, right? The case where everyone's value is independent and the case where everyone's value is correlated. And you could imagine modifying the mechanism, I think along the lines of what you're suggesting, which is that instead of predicting the average reported value, predict like the second sample moment, right? To try to get at the variance. And if our values are correlated, that will, I mean, values are correlated, that can mean a lot of things, but like in the simple model you could write down, if our values are correlated, that could incentivize you to acquire information. But the problem is in the independent case, right? So if our values are uncorrelated, BDM with betting will not incentivize information acquisition. And it happens to be that if we care about the average, that's fine, right? If the average has a sort of special property that if our values are uncorrelated, then you don't need information acquisition to learn about the statistic. But every other statistic, that's not going to be the case in general. So if we want to learn about the variance, then we're going to have trouble in the case where our values are uncorrelated, where BDM with betting will not incentivize information acquisition.
So if I understand, in this case, it's not so much robustness in the sense of for all equilibria, but more the distributions that creates problem for elicitation of this kind of.
Yeah, so it's both, right? It's certainly certainly we care about sort of robustness to these distributions, right? So in particular, we want a mechanism that works both for, in the case where values are independent and in the case where values are correlated. But we also sort of have the robustness to multiple equilibria, at least for our proofs, is important because of the possibility that you have mechanisms like, asking everyone what is the prior, and sort of punishing people if anyone deviates from a common report, which you saw in the intuition for theorem 1. So in that case, we did have this sort of this simple example where our values were all IID normal. And in that simple example, it would be easy to elicit the variance for that distribution if we could focus on our preferred equilibrium. But it's not going to be possible if we're not focusing on our preferred equilibrium if we care about robustness to multiple equilibria. So let me know if that's your question.
Thanks. Yes.
Okay. Anybody else? Just unmute yourselves if you have questions. Don't bother raising hands or anything like that. If not, maybe to get the audience, I suspect my question is, so let's stick with the independence case.
Yeah.
So you define an average as alpha plus beta, this expectation. So if you define it as just that expectation, I would have fully understood, but there's still this issue of the alpha and the beta. How is it that you can, I mean, maybe I'm missing some assumption here, but how is it that you can work those out as well?
So, so alpha and beta, just to be clear, these are parameters of the statistic. So these are something that the researcher will sort of say, the statistic that I'm interested in is the average for this alpha and this beta. So it's not something that you need to.
Okay, so I misunderstood. It's not that you can figure out an alpha plus beta of the mean. I mean, you could be interested in that, but it's not when I see what you mean. It's as if the alphas are chosen by the researchers and the betas. Yes, essentially, yes. Okay, fair enough.
So we're thinking basically about statistics that are essentially equivalent to the population's average value.
Yeah.
Yes, we'll list those as well, but any statistic that's meaningfully different, we're gonna have trouble. Yeah.
Okay. All right. Okay.
I have sorry, can I ask another question?
Sure.
I'm trying to make sure I understand. So suppose I don't know if that's allowed in the sigma statistic. I forgot the definition. Suppose you care about the median. Is that something I can do?
Yeah, so I think, so it depends on whether the median can be represented as a moment, which I'm not sure. Maybe it cannot. Yeah, one issue of the way that we've written this is that there are a lot of statistics that aren't moments. So the most obvious one is you might care about the entire preference distribution, right? And our results immediately translate to a negative result for that case. I imagine they might immediately translate to a negative result for the median.
Okay.
But the sort of as written, we're focusing on moments. So if the median cannot be represented as a moment, then the results as written don't have any.
Okay, I'm still going to ask about the median. So suppose you care about the median and you run your BDM betting thing, except that at the end you bet about the median of the reported things and not. In the independence case, I think I understand what goes wrong. What goes wrong in the case where there is some like the omega is like non-trivial?
So if there is correlation, it could work. It could work. Yeah. So like
so in some sense, the independence case drives
a hard case. Yeah.
Is the hard case. Okay. Okay.
Which is not what I initially thought, but I mean, so to be honest, what I had originally thought when we when we looked at this model, thinking about preference elicitation, what I had originally thought was that the BDM with betting mechanism could be extended along the lines that you and others have suggested to elicit basically any statistic. But it turned out the other way, right? It turned out that there was a very special property of the average, which is this to learn even if in the independent case. Yeah.
Okay, great. Thanks. That's helpful.
Thanks for the questions. Thank you everyone for the questions.
Can I sort of this is an aid to intuition, let's put it that way. I'm not suggesting this can be done, but so if one could, from just knowing the mean, somehow work out other moments, which basically are unworkable because they're non-linear functions of, the expectation of x squared is just not the same thing as the expectation of x squared. That's essentially the problem. That's what it boils down to, that if it's non-linear, I'm kind of a bit puzzled about your terminology about averages. I would call it the linear, a linear statistic, but you need linearity essentially because, and the problem we both know. So for example, if we felt that in some cases things could be approximated, we didn't want to, we could take linear approximations, maybe we could do something and stuff like that. So that's basically the intuition. Everything that's a linear function of the mean, you're okay. Anything that's not, you're not okay. And most of the moments we care about beyond the mean are not linear functions of the mean. And in particular, the median, I guess, is if you have a symmetric distribution, then it's equal to the mean, but otherwise you're in trouble, I suppose. That's it, right? That's the basic intuition about all of this.
Yeah. So I mean,
I hope I'm not trivializing it because I appreciate that I made it sound like, oh, that's it. But yeah.
Yeah. So the nonlinear versus linear distinction is at the core of why the independent case is hard for the nonlinear statistics, but easy for the linear statistics, right? So that's really the sort of the key observation when it comes to the negative results. Now, once you sort of move to the potentially complicated, correlated, heterogeneous world that we also need to accommodate in this model, then it becomes a sort of a non-trivial task to figure out why this BDM mechanism is able to elicit even the linear statistics. So I don't want to give the impression that linear statistics are easy to elicit. They're challenging to elicit, or at least to prove that we're able to elicit them. But they're trivially easy in the specific case with uncorrelated values. That is the hard case for nonlinear statistics. And if linear versus nonlinear is more evocative than average versus not average, that's I think a very reasonable point of view.
Okay. Actually, I think we can stop the recording now because we are at 1/4 past.